Okay, so in the last lecture, we have stopped at sorting algorithms, and exactly at quicksort. So our motivation again for doing quicksort is that we have reached merge sort, which was a log linear sorting algorithm with some problems, such as the use of big O and extra space. So, and then we started doing quicksort, which was yet another divide and conquer sorting algorithm, which works in very similarly to merge sort, but the partition of work is kind of the inverse of merge sort. Basically, we don't spend much work doing partitioning, or we spend the work doing partitioning and not much work doing the merging. And we have reached a conclusion that the worst case behavior of quicksort was n square, and the average case was n log n. And then we said that in order to make the algorithm even better, what we did was to choose the pivot at random, and then we reached the conclusion that by doing so, the worst case is still big O of n square, however with a low probability, whereas the average case is big O of n log n with a high probability. And we also saw the use of the median algorithm in the quicksort, and that it gives us n log n guaranteed performance in the worst case. However, the constant factor is quite high. So we have seen a lot of trade-offs concerning quicksort. But the last one that we said in practice, randomized quicksort, because we hardly see the worst case in practice, it's considered the best practical sorting algorithm available. I mean, for arbitrary sequences. However, after that, we are still stuck with the problem of space. Quicksort still requires extra big O fan space, because and that's due to basically when we do the partitioning, we scan through the sequence that we want to sort, and depending on where the pivot is, we are going to put some elements in a left sequence, and some elements in the middle sequence, and some elements in the right sequence. So as you can see, there is some displacement of elements in the sequence to the other sequences during the sorting. And this requires extra space. So if we have 20 elements, we require an extra space of 20 elements when we do this kind of partitioning. So we have not solved the problem of space with quicksort yet. So now we are going to see the new version of quicksort, which is in place. So an algorithm is in place when it does not require much extra space. So an in-place algorithm is an algorithm where the sequence stays inside the array, it doesn't go outside the array. For example, insertion and selection sorts, they are in-place sorting algorithms because we operate on the sequence inside the sequence itself, inside the array. We do not get out of we do not put the sequence somewhere else. Merge sort is not. Merge sort is not an in-place sorting algorithm because we need to put the sequence in another array. An in-place sorting algorithm might require extra constant or logarithmic space. For example, insertion sort, we still require constant extra space in order to store the different variables. Selection sorts as well, we need to store the min variable, the value variable. These are all variables we need to introduce in our algorithm, but they take constant space. Constant space meaning if we are sorting 100 elements, we need one extra variable. If we're sorting 1,000 elements, we still need one extra variable. So it's extra constant space, and that's perfectly fine. For divide and conquer algorithms like merge sort and quicksort, we do recursion, and in this recursion, when we make recursive calls, etc., we are actually we are actually consuming extra space by doing the recursion itself. Calling a function, when a function calls itself, that in itself is extra space. There is a stack associated and etc. So there is some extra space. If it is logarithmic, it's fine. We know that log of n is hardly an issue. We know that the log of a billion is, the log of a billion is 30, isn't it? The log of a kilo of 1,000 is 10, and the log of a million is 20, and a billion is 30. So even if we consume extra logarithmic space, that's hardly an issue. So an in-place sorting algorithm is the one where basically the amount of space needed outside the array is constant or logarithmic. So we will see now. So far, the version that we have seen about quicksort requires big of n extra space, so that this is not in place. Now we will see an in place version of quicksort, which is a little bit more complicated. Okay, it has these constraints. It is not randomized so far. We want to keep things simple so that we understand how this version of quicksort, the in-place quicksort, works. Okay, so it's not randomized. We assume that the sequence contains distinct elements, so we do not have like 7, 7. Okay, so each element only occurs once in a sequence, and later on we will see the general version. Okay, so we are starting with this version with these constraints. Elements are not duplicated, and this is not randomized, so that we understand how the quicksort works, the in-place quicksort works, and then we will see the general case. So the idea, this table is big enough for you, or? Okay. So the idea of in-place quicksort is the following. So again, I mean, if we remember how quicksort works, quicksort partitions the sequence recursively. So we first start with the initial sequence and partition it into two parts with respect to the pivot. And then we recursively partition each of the other parts in the sequence, if you see what I mean. So quicksort starts with the initial sequence. That's the idea of quicksort. That's the sequence. We partition it into three parts: pivot, less than pivot, and greater than pivot. And then this part, again, we recursively partition it. So here, this is a partitioning operation, and then there is a partitioning here, and there is a partitioning here, and so on. Okay. Now the partitioning is the problem, because we need extra arrays to put the elements after we compare them to the pivot. So this uses extra space. Now we are trying to find a partitioning algorithm which does not use extra space. So that's the thing. So in-place quicksort is the same as the other one. Okay, we are going to partition. We are going to recursively call the partitioning routine. So we partition here. We partition this sequence. We get this part. We get this part. We call quicksort here. We call quicksort here. We are still going to do the same thing. Okay. However, the partitioning is going to be different. We are not going to compare to the pivot, and if it is less, we copy it here. If it is more, we copy it here. Because this copying is causing us extra space. So the in-place algorithm is different from the other algorithm, which is not in place, is only different in the partitioning part. We are not going to copy elements over to a new array. We are going actually to just swap them inside the array. So in the new quicksort, in the in-place quicksort, what we will do, we have the sequence like that. What we do not copy elements. So we have a pivot, for example, here, and then we are going to work inside the sequence here. We are going to move elements from here. We're going to work inside the sequence here. We are going to move elements from here to here and from here to here until we get the partitioning. I mean, remember, the objective of the partitioning is at the end to have the sequence like that, to have the pivot here, to have these elements here which are less than the pivot, and to have these elements here which are greater than the pivot. So this is the objective of the partitioning. The way that we used to do it is to copy elements into new arrays, which costs extra space. This time, we are going to swap them inside the array. Now, the idea is the elements are going to be in different, I mean, there will be different elements inside this array that we want to partition. So what we are going to do, we are going to compare the elements one by one. Well, the general idea or the outcome is to have these elements. If there is an element which is larger than the pivot and is in this part, we are going to throw it over this part. Okay, so if the element here, so this is our initial sequence. Let's say the pivot is 5, and let's say that we have the following elements: 10, 9, 6, 1, 3. Let's say that the sequence, the initial sequence is like this, and this is our pivot. So if I ask you a question, what do you think after we partition this sequence into less than pivot, equal to pivot, greater than pivot, what is the sequence going to look like here? What is a possible solution for the sequence at the end? So I want to partition this in a way such that I have less than the pivot, and then pivot, and greater than pivot. So what's a possible solution here? What should this sequence look like at the end? Without knowing how partition works, but we know the objective of partition. Partition is to have the elements such that if the elements smaller than the pivot are to the left of the pivot, and the elements larger than the pivot are to the right of the pivot. So how does the sequence look like at the end, knowing the objective of the pivot, and the elements larger than the pivot are to the right of the pivot? So how does the sequence look like at the end, knowing the objective of partitioning? Okay, 10, 9, 6. Not necessarily in this order, okay? It can be 3, and then 1 instead of 1 and then 3. We are not making any assumption about the partitioning, whether or not it basically maintains the relative ordering of the keys, okay? A partitioning might or might not. The one that we have seen previously maintains the order of the keys. So if 10 is before 9, it's going to be 10 before 9. But here, it might not be the case. But that's not our problem. So we understand that partitioning that's our objective at the end. So the in-place sorting algorithm is going to look at the elements and then, for example, finds the element 10 here and then say 10 is greater than the pivot. It should not be in the left side. It should go over here. Okay? Okay? And then it looks, for example, at 9 and says 9 is bigger than the pivot. It should move over here. 1 is less, it should be in the left side. 3 is less, it should be here. So this is the way we are going to do the new in-place quicksort. Actually, what we are going to do more precisely is actually forget it. What we are going to do more precisely is we are going to look at the elements which are larger than the pivot and the elements which are smaller than the pivot and swap them. So that's large, that's small, we are going to swap them. And then that's large, that's small, we are going to swap them. If it is small, it stays here. If it is large, it stays here. At the end, we move 5 inside here. So that's the general idea. Okay? Partitioning means that the pivot is in the middle, and to the left, elements smaller than the pivot, to the right, elements larger than the pivot. Okay? And in order to achieve this goal, what we're going to do is we are going to move elements around inside. We are going to move elements around inside the array without getting out of the array. And the way we are going to do that, we are going to detect the elements which are larger than the pivot and those which are smaller than the pivot. If they are in their correct respective sides, so if the smaller are in the left side, they stay there. If the larger are in the right side, they stay there. If the smaller are in the right side, we move them over by swapping them with the larger items which are in the left side. Okay, so that's the general idea. Now let's look at it more in a more mechanical way, how it really works. So this is the sequence that we have been considering. Okay. So what we do, we are going to have 2 pointers. We are going to set the pivot. Let's say we are going to set the pivot to be the last element. Remember, the pivot here is not randomized. If it's not randomized, I am free to choose the pivot to be in any position I like, as long as I maintain the same position over the recursive calls. If I don't, then it's randomized. Okay? So I am choosing the pivot to be the last element of the sequence, and I am going to use 2 indices, left and right. So left is going to point to the first element, and right is going to point to the second last element. So when I say 9L, I mean there is a pointer left over 9, and there is a pointer R over 5. Okay, so this is just to make things easier for me to write. So 9L means there is a pointer called L, or an index called L, which is which is pointing to 9, and there is an index called R, which is pointing to 5. And remember, we said the objective is that we detect elements which are larger than the pivot. We throw them to the right if they are in the left. And if there are smaller elements than the pivot in the right, we throw them to the left. Okay? So the left index is going to start at the first element, 9. So 9 is it larger than the pivot, or is it smaller? So it's larger. Is it in the correct place, or should we throw it out the other way? We should move it the other way, right? Okay. So there is a loop. So we are going to move through the elements from here forward. Okay. If we detect an element which is larger than the pivot, we are going to stop. We are going to stop because we need to swap it later on. So this is an element. It has been detected to be larger than the pivot, so we're going to stop. Okay? We are going to stop right here. So L stays here. So do we move the left index? No, we stop because we have detected an element which is larger than the pivot. Now, we move now to the other index, which is the right. Now, the right is pointing to 5. Now, 5 is larger than the pivot, and it is in the right side. So, is it in the correct place or is it not? if 5 is larger than the pivot and it's here, it is in the correct place. I mean, we are not trying to sort the sequence, okay? Remember, we are trying to partition the sequence. Okay, so if we have 3, which is the pivot, and then 10, and then 5, this is good. 3, 5, 10 is also good. So we are not trying to sort the sequence. We are just trying to partition it. So this element 5 is larger than the pivot. So it is in the right place. It is in the right side. Forget about the pivot. We're not comparing with the pivot. We will swap at the end. Just look at this sequence here. Just look at this sequence here. Okay? Forget about the pivot. Just look at the sequence here. So we said 9 is larger than the pivot. So we are waiting because we need to move it. And then we look at 5. 5 is larger than the pivot, and it is in the right, so it's fine. Therefore, we are going to look at the next element to check if it is larger. We continue. If it is smaller, then there is something wrong. So we move 10. 10 is still larger than the pivot, so there's nothing to be done. It's still larger than the pivot, so there's nothing to be done. It is in the right place. It is in the right side. Okay? I mean, think of this as a sequence where things that are bigger than the pivot should be here. Things that are smaller than the pivot should be here. Go away. Oh. Okay? So this is what we're trying to do. We're trying, those that are bigger than the pivot should be in the right, and those that are smaller should be in the left. Okay? So again, 9 stays there, and then we've been at 5, it's larger, so it's fine. 10 is larger, so it's fine. 2 is smaller, it's not fine. Okay, so we stop. Now what do we do? Yeah, we are gonna swap that and that. So now we are here. So the smaller one now is in its correct place, it's in the left. The larger one is in its correct place, it's in the right. Okay? This is wrong. I will remove it later on, because this is something we do at the end of the partitioning, not here. So right now we are at this stage. Okay? And then we continue. So after the swapping, we resume. We are here now, so we move. Now, is 4 smaller than the pivot? No, so there is something wrong. So we're gonna wait. We're gonna wait right here, and then we move the right. Right is at 9. 9 is larger than the pivot, so we keep moving. 6 is larger than the pivot, so it's fine. We keep moving. 1 is smaller than the pivot, so something is wrong. So we stop. So we stop here, and we're gonna swap. Okay? And then we continue doing that until the loop ends. The loop, so let's go through this till the end. So again, so we're here, and we're here. 4 is larger than the pivot, we stop. 8 is larger than the pivot. 4 is larger than the pivot. Again, I'm lost here. So we are at 8. 8 is larger than the pivot, so something is wrong, so we stop. 4 is larger than the pivot, but it is in the right side, so we are fine. We keep moving. We find